Good day, I'm Arvin Enriquez, your subject teacher for Probability and Statistics. With this video lesson, we're going to discuss the topic, finding the mean and variance of the sampling distribution of the sample means. Our lesson objectives: at the end of this lesson, you are expected to find the mean and variance of the sampling distribution of the sample means, state and explain the central limit theorem, and defines the sampling distribution of the sample mean for a normal population when the variance is known and or unknown. Our lesson introduction: statisticians do not just describe variation of the individual values about the mean of the population. So we are not just describing, so we need to go more deeper on a statistical processes wherein we are assessing the behavior of these individual values that we can get from the mean of the population. Statistician also interested to know how the means of the samples of the same size taken from the same population vary about the population mean. So we're assessing or we are comparing two means from the samples that we can get from the same population or the same number of populations that we are dealing with. So what will be the behavior of these using the concept of your statistics, so we can assess this behavior and we can provide the right description for these means. For our discussion points, the properties of the sampling distribution of sample mean. If all possible samples of size n are drawn from a population of size n, your bigger n, that will be your population, your smaller n, that will be your sample, with mean mu and variance of sigma square, then the sampling distribution of the sample means has the following properties. First property: the mean of the sampling distribution of the sample means is equal to the population mean. So you need to take note of this. The mean of the sampling distribution of the sample means is equal to the population mean. So your mu sub of x bar is equal to your mu, meaning to say that your mean of the sampling distribution of the sample means is equal to the population mean. Next, properties. The variance of the sampling distribution of the sample means sigma is given. So there are times that your variance is given. So we need to use these two formulas. If the variance of the sampling distribution of the sample means sigma is given. So for finite population and infinite population, so there are two formulas for here. So one for finite population and one for infinite population. So for your finite population, so we need to use your sigma square of sub of x bar is equal to sigma square over n, which is your sample size, small n, multiplied by n, your bigger n, that will be your population, minus your sample here, which is your smaller n, all over your population, minus 1. So that is the formula for your finite population. So how about for your infinite population? So for your infinite population, we simply use this one. Your sigma square x is equal to, or should I say, your sigma square sub of x bar is equal to sigma square over n, which is your sample. This will be your formula for infinite population. For the third property, the standard deviation of the sampling distribution of the sample means is given by, so we can actually compute uh, the standard deviation of the sampling distribution using the following formulas. Also, one for finite population and another one for your infinite population. Here, as you can see in this formula, there's a sigma sub x bar, or we simply take the square root of this one. So taking the square root of this one, so that will be your um, formula for the standard deviation. So our formula is your sigma sub of x bar is equal to sigma square over square root of n multiplied by square root of n minus n all over n minus 1. This will be your formula for the finite population. And you need to take note that the square root of n minus n over your n minus 1 is the finite population corrector factor. So this will be your finite population correction factor, your square root of n minus n all over your n minus 1. So that will be your finite population correction factor. So for the next formula, that will be your sigma sub x bar is equal to your sigma over your square root of n for infinite population. So this will be your formula that we can use in computing the value of your standard deviation of the sampling distribution of the sample means is given by when you're dealing with your infinite population. So as you can see in your first formula, so we need to cancel these square assure or 2 assure exponent here because we need to take the square root of this formula from your variance. Taking the square root of your variance, so that will be whatever the value that we can get in getting the square root of your variance, that will be your standard deviation. So for the discussion points, let's deal with the concept of your central limit theorem. If random samples of size n, so that will be your sample, are drawn from a population, then as n becomes larger, the sampling distribution of the mean approaches the normal distribution, regardless of the shift of the population distribution. So what we need to do, or what we need to note about your central limit theorem is that, or we need to take note that the concept of limit theorem can provide us no, even if your n becomes larger and larger, or even your n gets or above 1,000 or more, again, even your n becomes larger and larger, is still your sampling distribution of the sample mean approaches the normal distribution. So again, with this concept of central limit theorem, n is not a problem. So whatever the value or n, or even your n becomes larger and larger, that's not, or that thing is not a problem, because the central limit theorem can provide you the concept even if your n becomes larger and larger, still your sampling distribution of the mean approaches the normal distribution regardless of the shift of the population distribution. So for example number 1, so consider the population consisting of 1, 2, 3, 4, and 5. Suppose samples of size 2 are drawn from this population. So there are 5 numbers given in this example number 1. So we're asked to describe the sampling distribution of the sample means. So for the solution to example 1, our step number 1 is that we need to determine the number of possible samples of size n is equal to 2. So how many possible samples that we can get from a size n which is equal to 2? So we need to adopt the concept of your uh, combination here. So here, your n combination of your small n, your bigger n combination of your small n. So that will be the total population. Your n is equal to, or your bigger n, your population is equal to 5. So there are 5 numbers being involved in your problem. So, and we're asked to determine the possible samples that we can get from a size n which is equal to 2. That's why your smaller n is equal to 2. That will be your sample. So how can we get the number of possible samples? By simply applying the concept of your combination. So that will be 5 combination of 2. So if we enter this 5 combination of 2 in your calculator, it can provide you a resulting value which is equal to 10. That's why the total number of possible samples that we can get in a size n which is equal to 2 from a total population of 5, that will be equal to 10. So there are there are 10 possible samples of size 2 that can be drawn from your population, which uh, there are 5 numbers being involved in our problem. So in your step number 2 for the continuation of the solution to example number 1, so we need to list all the possible samples and their corresponding means. First, in your first column, so this will be the list of all possible samples that we can get or we can draw, no, from the total population, which is equal to 5 and a sample size of 2. So there is an involvement of number 1, 2, 3, 4, and 5. So how many possible samples that we can get from a size 2? So here, in your first column, this will be the list of all possible samples. So first possible sample is that your 1 and 2, combination of 1 and 2. Next is combination of 1 and 3. Third is combination of 1 and 4. Your next is combination of 1 and 5 up to the combination of 4 and 5. So if we count this one, so that will be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So from step number 1, using the concept of your combination, so we can actually check or we can actually determine the total number of possible samples that we can get from the given values. No, in your second column, this will be the mean of the possible samples in your first column. So this is 1.5, meaning to say we need to get the average of these two numbers. So if we uh, compute for the average of 1 and 2, so that will be 3 over 2. So therefore, your mean is 1.5. So for the second possible samples, 1 and 3, so if we get the average of your 1 and 3, so that will be 1 plus 3 over 2, or simply equal to 2. So up to the last possible sample, which is equal to 4 and 5. Again, if we get the average or the mean of these 4 and 5, so that will be 4 plus 5 over 2. So your resulting value or the mean for this possible sample is equal to 4.5. Same process with the other uh, possible sample or from the list of possible samples that we can get or withdrawn from your given values or from your population. So as the continuation of the solution to example number 1 for your step number 3, so the construction of the sampling distribution of the sample means in the previous video lessons, we're done dealing with this one. So with the construction of the sampling distribution of the sample means, in your first column here, in your given table, these are values that reflect as a sample mean in your previous table a while ago. So these are values that reflect as a value of your mean in the previous table. Now, in your second column here, this will be the frequency. So how many times does this number in your first column reflect or reflected as the value of your mean in your previous table? So your 1.5 reflect once, then your 2 reflect once also, same with your 1.5. So up to the last value of your sample mean is equal to 4.5, which reflected once then. See, and your 2.5, 3, and 3.5 reflected twice in your previous table. Now, since from the concept of your combination, your 5 combination of 2. So meaning to say the total possible samples that we can get from the 5 numbers being given on the problem with the size 2. So that will be equal to 10. So this will be the total possible values that we can get from that, or the total number of possible uh, combinations that we can get from, or we can draw from the 5 numbers being involved in the problem. Now, in your probability, so this will be, well, whatever your values under your frequency, that that will be your numerator in your probability, or probabilities, I mean. So that will be 2, 2 here, 2, 1, and 1 here. Now, the question is that, sir, how we come up with the concept of this one, 1.5? A while ago, you said that your 2 as your frequency for your 2.5 is your numerator for your probability that we can map in your 2.5. Now, so this will be equal to 2 over 10. So if we get the lowest term of these 2 over 10, so that will be 1.5. Same thing with this one, same thing with this one, or the probabilities that we can map for your 3 and your 3.5. Now, again, the definition of your probability is your desired outcomes over your total possible outcomes. Since your 1 here is your desired outcomes, so that will be your numerator here, and 10 is the total possible uh, samples that we can get, or we can draw from the 5 numbers being involved in the problem. So that's why it's 1 over 10. Same thing with this 2 over 10. We just simply get the lowest term of these 2 over 10, since 2 and 10 are divisible by 2. So we can get the lowest term of this by simply dividing both your numerator and denominator by 2. So that will be equal to 1.5. Now, how can we check if the table is sampling distribution? So we need to get the total or sum of these probabilities under your third column. So if the total or sum of these probabilities under your third column is equal to 1, then the given table is a sampling distribution table. So that's how we check, if your table is a sampling distribution table, by simply getting the sum or total of those probabilities under your third column. Then if the total or sum of those probabilities is equal to 1, then the table is a sampling distribution table. Same concept with your probability distribution table. So as part of the continuation of the solution to example number 1, so for step number 4, so we need to compute the mean of the sampling distribution of the sample means your mu sub x. So follow these steps. So we need to multiply the sample mean by the corresponding probability and add the results. So as you can see in this table, in your first column, these are the values that reflect as the value of your sample mean in your previous tables. So in each sample means in your first column, there is a corresponding probability in your second column. So again, so whatever your values in your third column, this will be the product between your values in your first column and their corresponding probability in your second column. So we just need to multiply this value in your first column to their corresponding probability in your second column. So whatever the result or product between these two values, that will be your value that we can map for your third column. So 1.5 multiplied by 1 over 10, so that will be 0.15. So same thing with 2 multiplied by 1 over 10, so that will be equal to 0.2. Same with 2.5. 2.5 multiplied by 1 over 5, so that will be equal to 0.5. Same thing with 3 multiplied by 1.5, that will be equal to 0.6. Then 3.5 multiplied by 1 over 5, so that will be equal to 0.7. then 4 multiplied by 1 over 10, so that will be equal to 0.4, then 4.5 multiplied by 1 over 10, so that will be equal to 0.45. Now, whatever the value that we get from this one, so that will be the value of your mean. So we just simply get the total of these values under your third column, so that will be equal to 3. Meaning to say the value of your mean is equal to 3. So for example number 2, so consider a population consisting of 1, 2, 3, 4, and 5. So same values with our example number 1. Suppose samples of size 2 are drawn from these populations. So same thing, we apply the process of your combinations. So there are 10 as your total possible uh, samples that we can get or we can draw from these 5 numbers being involved in this problem. So compute the variance of the sampling distribution of the sample means. So right after in your example number 1, we compute for the value of your mean. So for this example number 2, we're just simply computing uh, the value of your variance for this kind of problem. So for the solutions of these or how we compute the variance of the sampling distribution of the sample means, we need to follow the following step. First thing to do is to subtract the population mean mu from each sample mean x bar, label this as x bar minus mu. Then next is to take the square of the difference between these two means, your population and your sample mean, label this as your x bar minus mu square. Then for letter C, multiply the results by the corresponding probability. Label this as f of x bar multiplied by x bar minus mu square. Then add the results. Now, here in your first column, that this will be your values for your sample means. In your second column, this will be your values of the probabilities that we can map in each value of your sample mean in your first column. Now, what will be the value in your third column? Will be the difference between your population mean and your sample mean. So since your sample mean is equal to uh, 1.5, then your population mean mu is equal to 3 as we compute in your previous slide that your population mean is equal to 3. Now, 1.5 minus 3 is equal to negative 1.5. So that will be your resulting value from the difference of 1.5 and 3. Then 2 minus 3, that will be negative 1. 2.5 minus 3, that will be negative 0.5. Then 3 minus 3 is equal to 0. Then 3.5 minus 3 is 0.5. Then 4 minus 3 is equal to 1. Then 4.5 minus 3 is equal to 1.5. So these 3 that we are subtracting in your from the values under your first column will be the value of your population mean as we compute a while ago in your previous table. Now, in your fourth column here under this table, there are values being reflected on this one. So this will be the square of your values under your third column. So that will be negative 1.5 square. So this will be your 2.25. Negative 1 square, that will be 1. Positive 1, because negative multiplied by negative, it's a positive value. The negative 0.5 square is a positive 0.25. So same up to the last value, that will be 1.5 square, or simply 1.5 multiplied by 1.5 is equal to 2.25. Now, in your last value or values under your fifth column, so this will be the product between your fourth column and your second column. So your second and your fourth column and your fourth column. Now, we just simply multiply this 1 over 10 to your 2.25. So that will be 0.225. 1 over 10 multiplied by 1, so that will be equal to 0.10 or 100. Then 1.5 multiplied by 0.25, so that will be equal to 0.05. Then 1.5 to 0, so that will be equal to 0. So same thing with this 1.5 to 0.25, 110 to 1, then 110 to 2.25. So this will be your resulting values now. So if we get the total of this one, so that will be equal to 0.75. Now, this will be the value of your variance. So we just simply uh, take the total or sum of those values under your fifth column. So whatever the total or sum of these values under your fifth column, so that will be the value of your variance of the sampling distribution. So meaning say for this problem, our variance is equal to 0.75. So for example number 3, a population has a mean of 60 and a standard deviation of 5. A random sample of 16 measurements is drawn from this population. Describe the sampling distribution of the sample means by computing its means and standard deviation. Assume that the population is infinite. So for the solution to example number 3, so there are 3 steps that we need to follow. First step, we need to identify the given information. So we need to list down all the given values. So your population mean is equal to 60, your population standard deviation is equal to 5, and your n, your sample size, is equal to 16. So find the mean of the sampling distribution. Use the property that your population mean of your sample means is equal to your population mean. Or should I say your sample mean is equal to your population mean. So we need to adapt this one. So meaning to say we are adapting this one. So we assume that the your population mean with respect to your sample means is equal to 60. Same value with your population mean as given in the problem. So find the standard deviation of the sampling distribution. Use the property that your sigma x of var or your sample mean is equal to sigma over square root of n. This is the formula for infinite population. So we assume that your population is an infinite uh, population. So how we compute for this standard deviation? So we just simply substitute the values of your population standard deviation, which is your sigma, and your sample size, which is equal to 16 now. Now, if we substitute these 5 and 16, so the simplified form is 5 over square root of 16. So since 16 is a perfect square, so if we take the square root of this 16, so that will be equal to 4. So we copy your numerator. So you just simply copy your numerator here. Then so that will be 5 over 4. Then 5 over 4, if we convert this 5 over 4 into fractions, so that will be equal to 1.25. So the value of your standard deviation now is 1.25, and your mean of the sampling distribution is equal to 60. In statistics, when your mean is higher than high value, then your standard deviation gets smaller and smaller. That's better. No, because when you say if there is a smaller value of your standard deviation, your data or your individual data from your population has a smaller interval between your individual data from your population. When you say they are not scattered. So the bigger value of your standard deviation will represent how scattered your individual data in your distribution. So if this standard deviation becomes smaller and smaller, that's better. Meaning to say, if we're talking about with the score of your student for a certain exam, meaning say if your standard deviation is 1 or less than 1, then your mean or the average of their scores is above average, for example 40, then your standard deviation is 1 or less than 1, meaning to say all students pass the exam and they are all above average. That's why it is better that you have your high value of your mean and a lower value of your standard deviation than to a higher value of mean with a higher value of standard deviation. So we need to look always for the value of your mean, which is higher or above your average, and your standard deviation uh, should be or must be a smaller value. It can be 1 point something or less. Much better if we can compute or we are arriving to that value of your standard deviation. So for your activity number 1 for this from this visual lesson, so consider all samples of size 5 from this population. So using these numbers, as you can see, this will be your 2, 5, 6, 8, 10, 12, and 13. With the sample size 5, you are asked to compute for the mean. List all samples of size 5 using the concept of your combination, then construct the sampling distribution, calculate the mean of the sampling distribution, and calculate the standard deviation. So there are 5 tasks here for you to accomplish. You need to compute for the mean, list all the samples of size 5, construct your sampling distribution, calculate the mean and standard deviation of the sampling distribution of the sample means. Then compare this to the standard deviation of the population. So you need to compute for the standard deviation of the population. Then you're comparing these values, no? You're going to compute for the value of the standard deviation from this sample. Then again, you just solve for the value of your standard deviation for the population. Then you need to compare these two values. So thanks for watching. If you want to like, comment, share, and subscribe, please do so.